Chapter 8, Section 3 again, Example 6. Well, here we are. I couldn't resist this. This is Larson's Far Side cartoon from quite a while ago. Of if you're going to get into heaven, here's St. Peter's asking you this motion problem to see if you can get in. I do like that he stops and asks if you need some paper, which is probably true. But here we go with word problems with motion, and they start with really a definition of what rate is. They kind of start here and say this is a first formula, but really rate means a fraction. It comes from the word ratio, which means distance, in this case distance over time. And you can solve this for different variables. If I solve this for d, I would multiply t times both sides, and I'm going to end up with this distance equals rate times time. And then if I solve for t, time, I get distance divided by rate, or distance over rate. And it's good to know this because when we get into these distance types problems, you're probably going to pick up the formula that is already solved for what you're looking for. Though again, this middle one is really the definition of a rate, which also relates to slope when we're talking about, usually we're talking about rise over run, right? If we graphed a rate problem, the distance would be usually our vertical change on our graph, and the time would be the horizontal change. So let's look at this, and again, we're working with systems of equations, so the goal is to create some equations so we can solve this problem. And we're getting, a little bit more complicated. In some ways, though, it's kind of a individual thing. Some people have a little more trouble with other types of problems. Usually the mixtures problems are tough to a lot of people. But these distance ones and multiple trains basically moving away from each other or towards each other, and these kinds of things can make it so probably the only way to solve these is with a system of equations. So remember that the goal is to create some equations, hopefully two equations with two variables, and then we can use our strategies to solve that. Well, let's go through this. A Vermont Railways freight train loaded with logs leaves Boston, heading to Washington, D.C. at the speed of 60 kilometers per hour. 2 hours later, an Amtrak Metroliner leaves Boston, bound for Washington, D.C. on a parallel track at 90 kilometers per hour. At what point will the Metroliner catch up with the freight train? So you have two trains moving at different speeds. They're going towards the same destination, but that's not, we don't necessarily know, or in fact that's what we don't know, is what distance will they travel when they actually catch up with, or the Metroliner catches up with the freight train. So familiarize, let's make a guess and check. Basically, a guess and check is usually, do I understand what kind of operations are involved to get information out of this thing? And here they say, well, let's suppose that they meet after traveling 180 kilometers. So they take something that we don't know, and that's what they're asking, is what point, basically what distance from Boston do these trains catch up with each other? Well, let's say we do know. Let's say that they did catch up with each other after 180 kilometers. And we want to calculate the time for each train to have traveled that far, right? So it's taking, when we do that, we're saying, well, I know distance, rate, and time, and I can use that to find out some things. So like the freight train, if it went 180 kilometers at 60 kilometers per hour, we would use this deal here where we're trying to find the time, which is time equals distance divided by rate. So you take 180 kilometers divided by 60 and you get a time of 3 hours. Well, the Metroliner would be the same thing because they meet, right? So they go the same distance. This one would go 90 kilometers per hour, and so how long would it take in travel time? Now is what they're talking about, is 2 hours. Well, would that work? And now that's the next part of this, is that they didn't leave at the same time, or that they would never really meet again. So there's that other part about this difference in the time that they left. And that's what they're talking about here. We see the distance cannot be 180 kilometers, since the difference of the travel times is not 2 hours. That would be the difference of their start times, right? Is that the Metroliner leaves 2 hours later. So if we kept on guessing and checking, we would be saying, well, the key is that we end up, not that the times are equal, but that they equal each other with the difference of the time. And what we're setting up is a algebraic expression to deal with this variable. And when you think about that, it says the distance at which the trains meet is unknown, but we do know that they will have traveled the same distance they meet. In other words, if I say d is distance, which I don't know, that's a variable, I know that distance will be the same for each train, which is very good to understand, is that I have this common distance between these two trains. So what about time? Now we don't know time either. So we should define the variables, and I think if you define the variables for the train, if you say the train that t, we say the time for the freight train is t, then well, they say thus time is equal to the number of hours that the freight train is running before they meet, and then t minus 2 would be the number of hours that the Metroliner runs before catching up with the train. So once they start, the freight train starts, time is ticking. The metro line is waiting, right? So if the train goes for 2 hours, then that's when the metro line does that. That they basically end up on, that they start moving at that point. There's a difference of 2 hours between those. So in other words, we're writing a variable for time, but also there's a difference in the relationship between the time. The freight train, if you say that's t, then how would we relate to the Metroliner time? Well, it leaves 2 hours later, or less than 2 hours of travel time is needed, right? And because it's going faster. So they start going through this and say, well, I can use some algebraic expressions for this. Time in the case of the Metroliner is t minus 2, and time for the freight train is t. D is the kilometers that they travel, which will end up being the same distance, so it's just d and d, and then here are the speeds that they give us. So if we put this into a table, we can start pulling out equations maybe, right? So we could say, well, a freight train is distance equals rate times time, right? So we don't know the d, but we have defined that as the distance it travels, which would be the same distance that the Metroliner travels. Its rate is 60 miles or 60 kilometers per hour, and t is time. We're not sure how long it takes. Well, the equation for the Metroliner would be the same d 90 kilometers per hour, and then the time is going to be 2 hours less because it starts out 2 hours later. So we end up with these two equations, basically both using distance equals rate times time. The real tricky part is to get the relationship between their times with this difference of 2 hours that happens because of their start times. So now we have two equations with two variables. We have a system of equations. Now this is really set up for substitution because both equations are already solved for one variable. And also when I think about this, they're going to go the same distance, right? They just have different ways that they get there, different rates and a different time model that it goes to. So we could say, the way they say it here is I can take the 60t and substitute it in for d here, and equal to be 60t equals 90 times the quantity t minus 2. And this is an equation with one variable. I can solve this, make sure you distribute, and I end up with, after they keep the t on the left side, which ends up having a negative, which is, I guess, is okay. I usually would avoid that. I probably would have added a negative 60t to both sides and 180 to both sides, and you would have got 180 equals 30t. But be careful with negatives. When I actually do a negative 1/30th times both sides, I end up with a positive 6. So what is that telling me? It's saying t is equal to 6. T is the amount of time for which train? That's the train, the freight train that left right away. So it traveled for 6 hours. And then I could say, well, how long would have the Metroliner have traveled for that? Well, it's going to be 2 hours less because it left 2 hours later. So it would be 4 hours. Now remember that the distance, not the time, is what they're asking for. So I could take that that first 6 hours and take it times the 60 kilometers per hour, and I would find out that this freight train actually traveled 360 kilometers. But a good check would be to check that with the other one. The other one traveled 4 hours at 90 kilometers per hour, and it would also have traveled 360 kilometers per hour. Now, you could fall into, it's kind of when you get to this point, say, well, I could have guessed and checked and got that and so on. But usually you don't get that, catch the complexity of this thing until you actually can write these equations. So and then remember to answer the question. A Metroliner catches up with a freight train 360 kilometers from Boston. Now they could have asked the question other ways too. The question could have said, how long did it take for the Metroliner, how long from the time, you'd have to do it in relationship to the freight train. You say, how long from the time the freight train left did it take for the Metroliner to catch it? And you'd say 6 hours. Or you could have asked the question, how long did the Metroliner train actually travel to catch the freight train, which would be 4 hours. So you could have the question come out in a lot of different ways, even though you did all the right steps to solve this. Make sure you answer the question that was asked.